Okay, so when you think about, the end of the dinosaurs,
Yeah.
probably the most famous extinction event in history, right? What's the first image that comes up?
Hmm.
For most people, I bet it's that giant asteroid hitting Earth, a massive space rock.
Right. That's definitely the big one everyone knows, the Hollywood version, almost. And look, it is a huge part of the story, probably the main trigger event, we now think. But the real story, when you dig into the science, the geology, it's way more complex and frankly, kind of more terrifying when you see all the pieces. It tells us so much more about how planets, how they respond to catastrophe, resilience, collapse, the whole system.
Exactly. And for decades, really, scientists were puzzling over the Great Dying, trying to pin it down.
Mm.
Now, after all this geological detective work, this paleontological forensics, we understand it wasn't just one thing. It was this catastrophic alignment of different forces, cosmic, geological.
Biological vulnerability, absolutely. It all came together in the worst possible way.
So today, our mission for you is to do a real deep dive. We want to get past just the meteor headline. We're going to unpack the 5 leading theories for the Cretaceous-Paleogene Boundary Event, the KPG. Used to be called KT, right?
That's right. KPG is the modern term. And we'll see how these different theories actually weave together into this devastating narrative. It's not necessarily one or the other.
Okay, but before we jump into how it happened, let's just grasp the scale. We're talking about a moment, a very sharp change, precisely 66.0 million years ago.
An abrupt moment in geological time, yes. And it's marked globally by this distinct layer in the rocks, the KPG boundary. It's thin, sometimes just centimeters thick, but you find it everywhere. And it screams planetary catastrophe.
And the cost, the sheer loss of life, is just mind-boggling. What are the numbers?
The conservative estimates, and these are conservative, show 75% or possibly more of all species on Earth vanished globally.
So 75%. That's not just the non-avian dinosaurs, the ones everyone thinks of.
No, not at all. It's the pterosaurs, those incredible flying reptiles that had dominated the skies for over 100 million years. Gone. The giant marine reptiles, mosasaurs, plesiosaurs ruling the oceans, gone. And the ammonites, those shelled cousins of squid and octopus, hugely diverse everywhere in the seas, wiped out completely.
So entire ecosystems just collapsed, almost overnight, geologically speaking.
Pretty much. A planetary reset button was pushed.
But here's the really fascinating part, the puzzle piece that any good theory has to explain. The extinction wasn't random, was it? It was selective.
Highly selective. That's the critical clue. It wasn't like a bomb going off and killing everything nearby. It acted like a complex environmental filter.
Okay, explain that filter. Who failed? Who passed?
Well, the victims tended to be the large animals.
Yeah.
Big bodies, high metabolic rates, often quite specialized diets. Think T-Rex. Huge predator, needed vast amounts of meat daily. Or giant herbivores tied to specific types of plants. When the food chain broke, they went first, quickly.
And the survivors.
Generally small, usually under, say, 25 kilograms, about 55 pounds. And critically, they were capable of sheltering somehow. Burrowing underground, hiding in caves, or being aquatic, semi-aquatic. And their diets were key too, generalists. Or detritivores, things that could eat decaying matter, seeds, insects, whatever was available.
Okay, but hang on. You mentioned sheltering, size, diet. What about something like a crocodile? They're large, they're predators. Why did they make it through when T-Rex didn't? That seems like a contradiction.
That's an excellent point, and it really sharpens the focus. Size alone wasn't the only factor. Crocodiles, alligators, turtles, they have a trick up their sleeve. They can go into a low metabolic state, brumation, hibernation.
Yeah.
They can essentially shut down and wait it out for months, even years, without food, especially in a protected aquatic environment.
So they could just sink into the mud and wait for the chaos to pass.
Exactly. Whereas a large, active, likely warm-blooded dinosaur with a high metabolism, it needed constant fuel. It couldn't just wait. The cold, dark conditions, the lack of food, that was fatal.
So the real filter was this new environment created by the catastrophe. Cold, dark, acidic, food scarce, favoring low energy needs and flexible diets.
Precisely. Any successful theory has to create that specific deadly environment on a global scale and explain why it favored, say, a burrowing mammal or a wading crocodile over a mighty T-Rex.
Got it. Okay, so let's dive into the theories. Theory number 1, death from above, the big one.
The Chicxulub impactor hypothesis. This is the heavyweight contender, the one that moved from a kind of wild idea to the scientific consensus over several decades.
And it all started back in 1980, didn't it? With Luis Alvarez, a physicist, and his son Walter, a geologist.
That's the seminal moment. They were studying rock layers around the KPG boundary in Gubbio, Italy. just looking at this thin clay layer separating the Cretaceous rocks below from the Paleogene rocks above, and they found something completely unexpected, something alien, anomalously high levels of the element, iridium.
Iridium. Okay, why is that significant?
Well, iridium is what we call a siderophile element, an iron-loving element. On Earth, most of it sank down into the planet's core when the Earth formed and was molten. So it's incredibly rare in the Earth's crust, like parts per trillion rare.
Okay.
But it's much, much more abundant in certain types of asteroids and meteorites, thousands of times more common than in Earth's crust.
So finding a massive spike of it right at the extinction boundary.
Exactly. They found levels up to 160 times the normal background concentration in that Gubbio layer. The logic was pretty direct. A huge asteroid, maybe 10 kilometers wide, must have hit the Earth. It would have vaporized on impact, and the debris, including all that asteroid-rich iridium, would have spread globally through the atmosphere, settling out to form this thin, iridium-rich layer right at the time everything died.
A truly global fingerprint of an extraterrestrial event.
Precisely. And that discovery just opened the floodgates. Since 1980, that same iridium anomaly has been confirmed at hundreds, literally hundreds, of KPG boundary sites all over the world. Deep-sea drill cores, rock outcrops on every continent. It's everywhere.
But you still need the crater, right? The actual impact site.
Yeah.
The smoking gun.
You do, and for a while, that was missing. But eventually, through geophysical surveys, mostly for oil exploration initially, scientists zeroed in on a massive buried structure. It's centered just off the coast of the Yucatan Peninsula in Mexico, buried under about a kilometer of younger sediments. The Chicxulub crater.
How big are we talking?
It's enormous, somewhere between 180 and 200 kilometers in diameter. That's roughly 110 to 125 miles across. Just a colossal scar.
And how did they confirm that was the KPG impact site?
By drilling directly into it, several scientific drilling expeditions have recovered core samples from the crater itself, especially from the peak ring. That's the ring of mountains that rebounds up in the center of very large impacts.
And what did those cores show?
Definitive proof of a hypovelocity impact. They found shocked quartz crystals with microscopic deformities only created by the immense pressures of an impact, pressures far beyond volcanic eruptions or earthquakes. They also found tektites, these tiny beads or blobs of glass, which are basically melted rock thrown out from the impact that cooled rapidly in flight.
And the dating matched.
Perfectly. Melt rock from within the crater structure dated precisely to 66.0 million years ago, right on the KPG boundary. And the confirmation got even stronger recently. Research in 2021 analyzing dust within the crater core itself found not just the iridium spike again, but the specific chemical fingerprint of the asteroid.
They could tell what kind of asteroid it was.
Yeah, they identified it as a carbonaceous chondrite asteroid, somewhere between 10 and 15 kilometers wide.
Why does the type of asteroid matter? Carbonaceous chondrite.
Because that type is known to be rich in volatile compounds. Things like water, carbon, and crucially for the kill mechanism, sulfur. This wasn't just a giant rock hitting, it was a giant rock carrying specific chemical agents that made the aftermath much, much worse.
Okay, so the evidence for the impact is overwhelming. Let's talk about what happened immediately after it hit. The first day.
Pure cataclysm. The energy release is almost incomprehensible. Billions of times the energy of the Hiroshima atomic bomb, all focused on one spot in an instant.
So first, the ground shakes.
Like nothing ever experienced in human history. The seismic shock would have been equivalent to a magnitude 11 or even 12 earthquake. Not just near the impact, but global tremors unlike anything we can imagine. Ripples through the entire planet.
And the blast itself.
Near the impact zone, an air blast traveling faster than the speed of sound, probably over 1,000 kilometers per hour. It would have flattened absolutely everything for hundreds, maybe thousands of kilometers around.
Then the fire.
Yes, the global firestorm. This is a key piece. As the impact blasted trillions of tons of rock and asteroid material upwards, much of it went on ballistic trajectories, arcing high above the atmosphere. When this material rained back down, re-entering the atmosphere all over the globe at high speed, the friction generated an intense pulse of heat radiation, like standing under a global broiler.
Enough to ignite fires everywhere.
Exactly. It ignited widespread, continent-spanning wildfires, and we see the evidence. Thick layers of soot and charcoal particles are found globally within that KPG boundary clay. It's the signature of a world on fire.
And it hit in shallow water, you said. So, tsunamis.
Mega tsunamis, unimaginably large waves, perhaps hundreds of meters high, radiating outwards from the impact site in the Gulf of Mexico. We find the geological evidence far inland. Massive, chaotic deposits called tsunamites, jumbled layers of sand, rock, deep-sea microfossils, and coastal debris, all mixed together hundreds of kilometers from the ancient shoreline in places like Texas, Alabama, even Haiti, and across the Caribbean. Evidence of colossal waves scouring the land.
It sounds like something out of a disaster movie, but the geological record confirms it.
And sometimes the record preserves moments with astonishing clarity. You mentioned sources describing the Tanis site.
Yes, in North Dakota. That
Yeah.
sounds incredible. Almost 3,000 kilometers away from Chicxulub.
Right. Tanis seems to preserve a snapshot of the minutes and hours immediately following the impact. It's a mass death assemblage. Fish, trees, land animals, marine organisms all jumbled together and buried rapidly.
How? What happened there?
The interpretation is that the immense seismic shock waves from the impact traveled through the Earth's crust incredibly fast. When they reached the shallow sea covering that part of North Dakota, the western interior seaway was still present then, they triggered enormous standing waves. Think of water sloshing violently back and forth in a giant basin. These are called sishes.
So huge inland surges of water.
Exactly. These waves swept inland, carrying marine life with them, ripping up trees and burying everything in thick layers of sediment almost instantly.
And the most amazing detail from Tanis.
The tektites. Those tiny glass beads formed from the impact melt rock. They found them lodged in the gills of fossilized sturgeon and paddlefish at Tanis.
Wait, so the impact happens in Mexico.
Rock gets vaporized and thrown into space.
Starts raining back down as molten glass maybe 15, 30 minutes later.
While these fish, thousands of kilometers away, are gasping for breath in the muddy water churned up by the earthquake's sisha waves.
And they inhale the falling tektites.
That's the evidence. It directly links the impact event in the Yucatan to mass mortality happening almost instantaneously, continent-wide. It's a geological crime scene frozen in time, a Rosetta Stone, as you said.
Unbelievable. But okay, as devastating as that first hours were,
Mm-hmm.
that wasn't the main killer for 75% of species, was it?
No. The immediate effects were horrific locally and regionally, but the truly global long-term killer mechanism was what came next. The long night, the impact winter.
And this connects back to the type of rock the asteroid hit.
Absolutely critical. This is where the specific location of the impact becomes the geological worst-case scenario. Chicxulub didn't hit deep ocean or solid granite. It hit a shallow marine platform made of thick layers of limestone, calcium carbonate, and crucially evaporate deposits rich in sulfur rocks like gypsum and anhydrite.
Why is sulfur so bad?
Because when the impact vaporized those rocks, it didn't just blast dust and soot into the atmosphere. It released hundreds of billions of tons of sulfur gases, primarily sulfur dioxide, SO2, directly into the stratosphere. Far more sulfur than a typical impact into silicate rocks would have produced.
And what does that much sulfur do way up there?
It reacts with water vapor to form tiny droplets of sulfuric acid, creating sulfate aerosols. These aerosols are incredibly effective at reflecting sunlight back into space.
So it's like a giant sunshade.
The planetary scale sunshade, yes. This stratospheric shroud of dust, soot, and especially sulfur aerosols blocked a huge percentage of incoming sunlight. Not just for days or weeks, but likely for years, possibly even decades, according to some models.
Years without significant sunlight.
Global temperatures plummeted. Earth was plunged into a freezing, prolonged winter, regardless of season or latitude.
And the effect on life.
Catastrophic collapse of the food web, starting at the very bottom. Photosynthesis stopped, or was drastically reduced, both on land and in the oceans. Phytoplankton, the base of the marine food web, died off en masse. Terrestrial plants withered and died in the cold and dark.
So the herbivores starved first.
Exactly. No plants, no food for the giant sauropods or hadrosaurs. They starved.
And then the carnivores that preyed on them.
They followed soon after. The entire food pyramid collapsed from the bottom up.
And this explains the selectivity we talked about earlier.
Perfectly. If you're a large animal with a high metabolism, needing constant large amounts of food, you can't survive years of darkness and starvation. Game over.
But if you're small, maybe you can hibernate, or you eat insects or roots or decaying leaf litter.
You have a chance. You can shelter from the cold, maybe in a burrow. Your energy needs are lower. You can wait it out, scavenging what little is available. It favors the small, the generalist, the low-energy organism.
What about the acid-rain connection? You mentioned sulfur.
Right, those sulfur aerosols eventually fall out of the atmosphere, but they combine with atmospheric water to create sulfuric acid, widespread, intensely corrosive acid rain. This would have further damaged any surviving vegetation on land, and crucially, it would have rapidly acidified the surface layers of the oceans.
Making it hard for things to form shells.
Devastating for organisms that build shells or skeletons out of calcium carbonate. Plankton, corals, ammonites, certain types of clams. The acidification would have made it difficult or impossible for them to build their structures, adding another layer of stress, especially in the marine realm.
So Theory 1, the Chicxulub impact, gives us the instant cataclysm, the pulse, and this very specific kill mechanism, the impact winter plus acid rain, that explains the global reach and the selectivity of who lived and who died.
That's the core argument for the impact hypothesis, and the evidence is incredibly strong. It provides the knockout blow.
Okay, but you said earlier it's more complex, so we need to bring in Theory 2. Because amazingly, the asteroid wasn't the only massive geological catastrophe happening around that time.
Not even close. While the impact was the sudden shock, there was a much longer, slower burning, but equally potent disaster unfolding on the other side of the planet. The Deccan Traps volcanism. A world on fire, but this time from within the Earth.
The Deccan Traps, located in modern India, right?
Correct. And when we say volcanic province, we're not talking about a single Mount St. Helens or Pinatubo. This is one of the largest volcanic features on Earth.
And these weren't cone volcanoes.
No, these are flood basalts. Imagine enormous fissures opening up in the Earth's crust, kilometers long, and just pouring out unbelievable volumes of low-viscosity basaltic lava. Not explosive eruptions, mostly, but continuous, massive outflows.
Just how massive are we talking?
The scale is staggering. Over a period of less than 1 million years, centered around the KPG boundary, the Deccan eruptions unleashed an estimated 1 million cubic kilometers of lava.
1 million cubic kilometers. I can't even picture that.
Think about covering an area the size of modern France or Spain, maybe 500,000 square kilometers, with layer after layer of solidified lava, reaching thicknesses of up to 2 kilometers in some places. It's immense.
But like the impact, the lava itself wasn't the global killer, was it? It was the gases.
Primarily, yes. Just like the impact vaporized rock, these massive, sustained eruptions released colossal quantities of volcanic gases into the atmosphere over a very long period. This wasn't an instant shock. It was a long-term, multi-stress assault on the global climate system.
What were the main culprits, gas-wise?
2 big ones, with opposing effects which created chaos. First, carbon dioxide, CO2. Flood basalts release enormous amounts of CO2. Over hundreds of thousands of years leading up to the KPG boundary, this sustained CO2 release caused a significant long-term global warming trend. Studies suggest temperatures may have risen by as much as 7 or 8 degrees Celsius, a planetary heat wave.
So the world was already getting uncomfortably hot before the impact.
Significantly warmer, yes, chronic stress number 1. But then you have the other major gas, sulfur dioxide. SO2, the same villain as from the impact, but released volcanically.
And SO2 causes cooling, right, by forming those reflective aerosols.
Exactly. So while the background trend was CO2-driven warming, the Deccan eruptions occurred in pulses. Each major pulse would have also released huge amounts of SO2, creating sulfate aerosols in the stratosphere. These volcanic aerosols would cause episodes of rapid, severe, but relatively short-term global cooling volcanic winters, and also contribute to intense acid rain, just like the impact aerosols.
So the climate was swinging back and forth wildly.
That's the whiplash climate concept. Imagine living through long periods of intense greenhouse heat, punctuated by sudden, sharp plunges into volcanic winter and acid rain. Back and forth, back and forth. Ecosystems, especially complex ones with large animals adapted to stable conditions, just can't cope with that level of relentless instability. Seasonal cues go haywire, food sources appear and disappear unpredictably. Adaptation becomes almost impossible.
Constant stress.
Constant destabilizing stress. And it wasn't just the climate. That CO2 being pumped out was also being absorbed by the oceans.
Leading to ocean acidification, like with the impact aftermath.
Yes, but this was a slower, more chronic acidification happening for millennia before the impact delivered its acid pulse. It was pre-stressing marine life, making it harder for plankton, ammonites, corals to build their shells and skeletons. They were already weakened.
Is there other evidence for the Deccan's global reach?
Yes, there's a chemical fingerprint in the rocks. Mercury. Massive volcanic eruptions like the Deccan release significant amounts of mercury vapor. Scientists find distinct spikes in mercury concentrations in sedimentary rocks laid down globally around the time of the KPG boundary. And crucially, these mercury spikes correlate very closely with the timing of the most intense pulses of Deccan volcanic activity. It's like a global pollution signal from the eruptions.
So the planet was being poisoned from within, even before the asteroid hit.
It was definitely under severe escalating environmental stress from the Deccan traps for a long time.
Now, some scientists argue the Deccan traps weren't just a contributing factor, but the main cause of the extinction, right? Like Gerda Keller.
That's correct. There is a minority viewpoint, argued forcefully by Professor Keller and others, that the extinction was primarily driven by the cumulative effects of Deccan volcanism over hundreds of thousands of years, and perhaps wasn't as instantaneous as the impact model suggests.
What's their evidence for that?
They point to some geological sites where they interpret a time gap between the layer containing the impact debris, like tektites or the iridium spike, and the main layer where the mass extinction of fossils, particularly marine microfossils, seems to occur. They suggest this gap could be up to 150,000 years in some places.
Implying the impact happened, but life mostly carried on for a while, only succumbing later to the volcanic effects.
That's the core of their argument, that the volcanism delivered the prolonged stress that really caused the ecosystem collapse, perhaps pushing life over the edge gradually, rather than an instant impact kill.
And they also point to other mass extinctions.
Yes, they highlight that other major extinction events in Earth's history seem strongly linked to massive flood basalt eruptions, without clear evidence of a simultaneous giant impact. The most famous example is the end Permian extinction, the Great Dying, about 252 million years ago. That event, which wiped out maybe 95% of marine species and 70% of land vertebrates, coincides precisely with the eruption of the Siberian Traps flood basalts. So there's historical precedent for volcanism alone causing mass extinction.
It keeps the debate alive and ensures we scrutinize the timing and effects of both events really carefully.
Absolutely. Healthy scientific debate. Though the vast majority of evidence now points to the impact as the primary trigger at the boundary, the Deccan context is essential.
Which leads us smoothly into Theory 3, this idea of a slow decline. That maybe the dinosaurs and other Cretaceous life were already on their way out, weakened, before either the volcano or the asteroid delivered the final blow.
Right. This theory suggests the catastrophes might have just pushed over an already teetering system. The idea is that the late Cretaceous biosphere wasn't necessarily thriving right up until the KPG boundary.
What would have caused such a long-term decline?
One major factor often cited is a significant drop in global sea levels during the last few million years of the Cretaceous, the late Maastrichtian age. This is called marine regression.
Sea levels went down. How does that affect life on land or dinosaurs?
Well, throughout much of the Cretaceous, sea levels were very high. Huge, shallow inland seas covered large parts of the continents. The Western Interior Seaway cutting North America in half is the classic example. These shallow seas created vast areas of highly productive coastal plains and marine habitats, and they also moderated the global climate, keeping it generally warm and stable.
Okay, so when sea levels dropped,
those shallow seas drained away. That's a massive loss of productive habitat, both marine and coastal. On land, it meant coastlines retreated and the interiors of continents became larger, more exposed. This likely led to increased seasonality, bigger temperature swings between summer and winter, perhaps drier conditions in continental interiors, less stable, less uniformly warm climates than what the giant dinosaurs and lush flora had evolved in.
So habitat loss and climate becoming less hospitable, chipping away at populations over millions of years.
That's the idea. Chronic environmental stress from changing geography and climate.
Is there fossil evidence for this decline? Were there fewer dinosaur species around just before the boundary?
This is where it gets really debated. Some studies, especially looking at the rich fossil record of the latest Cretaceous in Western North America, have suggested a decrease in dinosaur diversity, fewer species present in the last 1 or 2 million years before the impact. Similar analyses of fossilized dinosaur eggshells from sites in China have also been interpreted as showing lower biodiversity towards the end.
So the hypothesis combines these factors: habitat shrinking due to sea level fall, plus the ongoing climate stress from the Deccan traps, putting populations under strain, making them less resilient, fewer in number, maybe less genetically diverse.
Priming them for collapse when the big shocks finally hit. They didn't have the numbers or the robust ecosystems to bounce back.
But you said this is heavily debated. What's the counter-argument?
The big counter-argument is that the perceived decline might not be real. It could be an illusion, an artifact of how the fossil record itself is preserved. This is the senior ellipse effect we touched on earlier.
Remind us what that is again.
Because fossils are rare, the last known fossil we find of a species in the rock layers is almost certainly older, maybe much older, than when the very last individual of that species actually died, especially if the species was becoming rare towards the end.
So the record stops before the extinction actually happens.
Exactly. And if the quality of the rock record itself gets worse as you approach the extinction boundary, meaning fewer rocks are deposited that are good at preserving fossils, then it will look like diversity is dropping, even if the animals were still there.
And is there evidence the rock record does get worse near the KPG boundary?
Yes, particularly in North America, where many of these decline studies are focused. The types of environments that best preserve dinosaur fossils, like river floodplains and deltas, seem to become less common or are subject to more erosion in the rock layers immediately preceding the boundary.
So I find fewer fossils, which looks like a decline, but it might just be because the recording tape of the rocks got patchy.
Precisely. It's a geological bias, potentially creating a false biological signal. Distinguishing a true decline from this artifact is one of the major challenges.
How do scientists try to resolve that?
By looking at different types of fossils with better records, like microscopic marine plankton or plant pollen, which are often preserved more continuously, and overwhelmingly, those records show an incredibly abrupt, catastrophic extinction event happening exactly at the iridium layer, right at the KPG boundary. That massive sudden die-off argues against a long, slow, gradual decline being the primary driver. It suggests that while late Cretaceous ecosystems might have been stressed, they were largely intact until the impact delivered the killing blow. The decline, if real, likely just lowered the resilience threshold.
Okay, that makes sense. The suddenness points away from a slow fizzle. Which brings us then to Theory 4. This feels like where it all comes together. The perfect storm, the press-pulse synthesis.
Exactly. This is the modern consensus view. It acknowledges the power of both the Chicxulub impact and the Deccan Traps volcanism, and sees them not as competing theories, but as complementary, potentially linked parts of the same devastating event.
So the press-pulse model. Explain that framework.
It's a really useful ecological concept. The press represents the long-term chronic environmental stress. In this case, that's primarily the Deccan Traps volcanism, the warming, the ocean acidification, the mercury poisoning, the wild climate swings. All of this was pressing down on the biosphere for hundreds of thousands, maybe millions of years, weakening ecosystems, reducing biodiversity, eroding resilience.
Okay, so the planet was already sick, running a fever, unstable.
Metaphorically, yes. And then comes the pulse. The sudden, acute, catastrophic shock. That's the Chicxulub impact. The instantaneous devastation, the global wildfires, the tsunamis, and most importantly, the years-long impact winter that shut down photosynthesis.
So the press weakened the system, and the pulse delivered the knockout blow.
Precisely. The key insight is that the combined effect was far, far worse than either event likely would have been on its own. The whole was much more devastating than the sum of its parts.
If the impact had hit a perfectly healthy, stable planet, maybe the extinction wouldn't have been so profound.
It's plausible. The ecosystem might have had more resilience, more refugia, more ability to bounce back from the impact winter if it hadn't already been suffering from the Deccan press.
And conversely, if the Deccan volcanism had continued without the impact, maybe life would have adapted gradually, or the extinction would have been less severe or selective.
Also possible. The impact provided that incredibly sharp global environmental filter that the volcanism alone might not have achieved so suddenly.
But now, the really mind-blowing part of this synthesis, the idea that these two catastrophes might actually be linked, that the impact could have influenced the volcanoes.
This is a fascinating and relatively recent area of research, but the evidence is building. The hypothesis is that the sheer seismic energy released by the Chicxulub impact, remember, equivalent to a magnitude 11 or 12 earthquake globally, could have significantly affected volcanic systems worldwide.
How? Just by shaking things up.
Essentially, yes. Imagine shock waves from the impact traveling through the Earth's mantle. The idea is that these incredibly powerful seismic waves could have disturbed the vast magma plumbing system feeding the Deccan Traps, which were located roughly on the opposite side of the planet, near the impact's antipode.
Like hitting one side of an orange and seeing the other side bruise.
A decent analogy. The shaking could have triggered increased magma melting, opened up new pathways for magma to reach the surface, or simply allowed existing magma chambers to erupt more violently and voluminously.
Is there evidence for this in the timing of the eruptions?
There seems to be. High-precision geochronology dating the different layers of Deccan lava flows very accurately suggests that while the Deccan traps were definitely erupting before the impact, the single largest pulse of eruptions happened after the impact.
How much larger?
Some studies estimate that around 70 to 75% of the total volume of the Deccan lava erupted in a relatively short period, perhaps just 30,000 to 50,000 years, beginning very soon after the Chicxulub impact.
Wow. So the impact might have basically thrown gasoline on the Deccan fire.
That's the compelling implication. The impact didn't start the Deccan eruptions, but it may have dramatically intensified them, triggering the most massive phase of volcanic activity right when the biosphere was reeling from the impact winter.
Creating a kind of synergistic hell.
Exactly. You get the impact winter, cold, dark, starvation, then almost immediately you get this massive surge in Deccan volcanism, pumping out colossal amounts of CO2, driving intense, prolonged greenhouse warming after the cold snap.
So there's no stable refuge, no chance to recover. First freeze, then fry.
Pretty much. The ecosystem was hit by devastating cold and darkness, and then, before it could stabilize, slammed by runaway greenhouse warming and continued ocean acidification from the volcanoes. The Deccan traps, potentially amplified by the impact, effectively removed the planet's ability to bounce back quickly.
That paints a truly terrifying picture of compounding disasters.
Mm-hmm.
Okay, so the press pulse synthesis, possibly with a direct link between the two, seems like the most complete explanation.
It integrates the most evidence, yes, but science always considers alternatives. So let's briefly cover Theory 5, the other ideas, alternative and contributory mechanisms.
This is where we look at things that have been proposed but maybe haven't held up to scrutiny or might be minor factors.
Right. It shows the scientific process testing hypotheses, discarding ones that don't fit the global evidence.
Okay, what about purely biological causes, like disease?
Disease or epidemics are often suggested, especially in popular accounts. But as a primary driver for a global mass extinction, highly unlikely. Think about it. What single disease could simultaneously wipe out giant land dinosaurs, tiny marine plankton, flying pterosaurs, shelled ammonites across every continent and ocean at the same time? Pathogens are usually much more specific. It just doesn't fit the breadth of the KPG extinction.
Makes sense. What about those weird eggshells, pathological eggshells?
Yes. Findings mainly from France and Spain showed some late Cretaceous dinosaur eggshells that were unusually thin or had multiple layers suggesting problems with reproduction. For a while, this was floated as a possible cause widespread reproductive failure, but it's now mostly seen as evidence of localized stress in those specific regions, maybe due to the environmental effects of early Deccan volcanism or regional climate change. It wasn't a global phenomenon capable of causing the entire extinction.
But you mentioned a more modern biological link earlier related to the impact winter.
Yes, the vitamin D3 deficiency hypothesis. This one is much more plausible and directly links the impact's environmental effects to dinosaur physiology.
Remind us how that works, the lack of sunlight.
The impact winter, caused by the dust and aerosols, would have blocked not just visible light, but also solar ultraviolet B radiation UVB, possibly for years. Many reptiles, and likely dinosaurs were similar, rely on UVB exposure on their skin to synthesize vitamin D3 or cholecalciferol.
And vitamin D3 is important for it.
It's absolutely essential for calcium metabolism. That means strong bones, healthy growth, and critically, for females, mobilizing calcium to form strong eggshells and for proper embryonic development inside the egg.
So no UVB means no vitamin D3 means reproductive chaos.
Potentially, yes. A prolonged lack of UVB could have led to widespread reproductive failure. Eggs might not have formed properly, shells could have been too thin, or embryos might not have developed correctly, dying in the egg. It's a very specific vulnerability of large egg-laying reptiles to the precise environmental consequence prolonged darkness of the impact.
That's quite elegant, linking the physics to the biology.
Yeah.
What about the old idea that mammals outcompeted the dinosaurs?
Completely discredited. While mammals did survive and then rapidly diversified after the dinosaurs were gone, during the Cretaceous they were almost all very small, shrew or rat-sized, mostly nocturnal insectivores or omnivores. They coexisted with dinosaurs for 150 million years without ever challenging their dominance. There is simply no way these small mammals could have driven the global extinction of creatures like T-Rex or Triceratops or marine reptiles or ammonites. They were opportunistic survivors, not giant killers.
Right, their time came because the giants vanished.
Exactly. The extinction opened the door for the age of mammals.
Any other fringe ideas worth mentioning? Supernova?
The supernova idea was proposed early on. A nearby star explosion showering Earth with cosmic rays altering climate. But it doesn't fit the evidence. A supernova would leave behind specific radioactive isotopes, like plutonium-244 or iron-60, which have very long half-lives. These have not been found consistently at the KPG boundary. What is found globally is that iridium anomaly, which points strongly to an asteroid or comet from within our solar system, not a distant stellar explosion.
And things like dinosaurs just got too big or too stupid evolutionary senility.
Those are outdated, frankly nonsensical ideas that completely fail to explain the mass extinction aspect. Why would ammonites or plankton care if dinosaurs got too big? It ignores the global multi-phylum nature of the event. The extinction required a global environmental catastrophe, not just dinosaur-specific problems.
Okay, so wrapping this all up, we've gone through the impact, the volcanoes, the potential decline, the synthesis, the alternatives. For our listeners trying to grasp the full picture, what's the final verdict from the science today?
The current scientific consensus is clear, though nuanced. The Chicxulub impact was the pulse. It was the primary trigger, the knockout blow delivered right at the KPG boundary. The impact winter mechanism, driven by sulfur aerosols from vaporized Yucatan rock, provides the best explanation for the sudden, global, and highly selective nature of the extinctions. The evidence for this is overwhelming.
But it didn't happen in the vacuum.
Absolutely not. The Deccan Traps volcanism was the crucial press. It represents the long-term environmental stress that destabilized the biosphere for potentially hundreds of thousands of years leading up to the boundary. The warming, the acidification, the climate whiplash, this eroded resilience and made the ecosystem far more vulnerable to the impact's shock.
The two events might be directly linked.
The evidence suggesting the impact's seismic energy dramatically intensified the Deccan eruptions is compelling and fits the timing well. This turns it from two separate disasters into a linked, compounding catastrophe. The impact hit a planet already stressed by volcanism and then potentially made that volcanism even worse in the immediate aftermath.
So it wasn't just bad luck with an asteroid, it was maybe the worst possible timing for that asteroid to hit, given the state of the planet.
That seems to be the case. A catastrophic alignment of cosmic and terrestrial forces hitting a biosphere already pushed towards its limit.
So what does this all mean? What's the legacy of the KPG event beyond just killing the dinosaurs?
It was profound. It wasn't just an ending. It was a planetary reset that enabled a new beginning.
A creation event, almost.
In a way, yes. By completely removing the dominant large vertebrates, the non-avian dinosaurs on land, the giant reptiles in the sea, it created this enormous ecological vacuum across the entire planet. Niches that had been filled for 150 million years were suddenly empty.
And who stepped into that vacuum?
Our ancestors. The small, often nocturnal, burrowing mammals that managed to survive the impact winter, likely because they were small, adaptable, maybe ate insects or seeds or roots. With the dinosaurs gone, they faced less competition, less predation.
And they diversified like crazy.
Explosively. The Paleogene period, immediately after the extinction, sees this incredible radiation of mammals, diversifying into all the ecological roles previously held by dinosaurs, large herbivores, large predators, tree dwellers, swimmers. This is the dawn of the age of mammals.
Leading eventually to primates and us.
Ultimately, yes. The KPG extinction directly paved the way for the evolution of Homo sapiens. Without that asteroid and the ensuing chaos clearing the slate, the world today would likely look vastly different, possibly still dominated by dinosaurs or their descendants. We owe our existence in a very real sense to this catastrophe.
That's a humbling thought. So reflecting on this deep dive, what's the final takeaway message for us, looking back from 66 million years later?
I think the KPG event serves as a powerful, deep-time case study in planetary resilience and tipping points. It shows that even a complex, established biosphere can collapse incredibly quickly under the right or perhaps wrong combination of pressures. Specifically, it highlights the danger of chronic, long-term environmental stress, the press. While ecosystems might seem to cope with gradual change for a while, that underlying stress can erode their resilience, making them incredibly vulnerable to sudden acute shocks the pulse. The Deccan Traps primed the pump. The Chicxulub impact pulled the trigger.
Which leads to a final provocative thought for you, our listeners. Considering our planet today in the Anthropocene, what chronic long-term environmental pressures, what presses are we currently applying to the global ecosystem? Climate change, habitat loss, pollution, biodiversity decline. How might these ongoing stresses be reducing the planet's resilience, potentially priming it for catastrophic failure if faced with an unexpected future pulse, whether natural or human-induced?
It's a complex question with no easy answers, but understanding the dynamics of past events like the KPG extinction gives us a crucial framework for thinking about the fragility and the future of our own world.